Hi, my name is Manish Gupta, and in this video, I'm going to talk about this model called as Neural Corpus Indexer, which is a model for document retrieval. So what is NCI's model architecture, right? What is it? What is NCI or the Neural Corpus Indexer model meant to do? So it is a model which is meant for retrieval systems. It's a model which is different from sparse retrieval or dense retrieval. Remember, in sparse retrieval, the idea is to index documents using an inverted index and then do a token-wise lookup given a query, right? In dense retrieval, the idea is to essentially index the documents into an approximate nearest neighbor index and then when a query comes in, you essentially retrieve documents with highest similarity by doing a similarity search on this approximate nearest neighbor lookup index. Now, NCI actually asks an interesting question. How about not having an index at all? Or how about actually using a large language model as an index by itself? And that is why it's called Neural Corpus Indexer. So it basically uses a model to index, to act as an index in that sense. So NCI is basically a sequence-to-sequence neural network that generates relevant document IDs given a query. So the idea is that this encoder-decoder kind of a model, which is transformer-based, is going to take the query as input, query tokens as input, and then it's going to basically generate relevant document IDs as output. Now, of course, it can't generate full documents, and therefore it's going to generate document IDs. So this basically means that it must first be able to represent each document in the collection using document IDs, right? So accordingly, NCI actually has three different components: pre-processing, query generation, and the training pipeline that you see at the bottom, right? So in the pre-processing time, essentially, it takes all the documents, embeds them, and then does a hierarchical k-means algorithm to generate a semantic identifier for each document. The broad idea, the broad intuition is that when you come up with an ID representation for a document, uh, documents which are similar to each other should have similar IDs. And therefore, what you do is to basically do embedding and then do k-means clustering. But you do in a hierarchical manner. Therefore, each document is basically going to be represented as a list of clusters. So essentially, if I were to talk about this particular document, document ID 705, well, it's going to be represented with a number at this level, another number at this level, and then the third number at this level in a three-level hierarchy that you see here, right? So broadly, the way this hierarchical k-means works is as follows. You basically take all the documents, you embed them, and then you compute I mean, at the top level, of course, all the documents belong to the one cluster, the top cluster, and then you try to compute k different clusters at the next level. So you use k-means to actually split these documents into k different clusters. Further, all the small clusters smaller than a particular threshold are further split. So the second level split, you do the second level split by again doing k-means within this particular cluster only. Right? So that is how you basically obtain an entire hierarchy. It's a top-down method to essentially get a hierarchy of clusters using hierarchical k-means. Right? Now, let's say this blue dot is basically cluster number 5 here. This one is basically cluster number 4 here, and this is probably cluster number 2 here. There are more documents in this cluster. So therefore, this particular document is essentially, of course, the leaf level cluster has only one document. So this document is going to be represented using this, this list as the document ID for it. So the document ID is basically a list of cluster IDs across different levels of clustering in the across different levels of clusters in the hierarchy as generated by the hierarchical k-means. Okay. Now, the next step is to basically be able to train a sequence-to-sequence learning model. However, if you were to just train a sequence-to-sequence learning model on query document click data, right? I mean, which queries are relevant to which documents, in that case, you may not have too many queries for which the document is relevant. A particular single document is relevant, right? And remember, you cannot really represent documents using their terms. They're just being represented using numbers. So you really want a very, very dense graph of query document relevance. To be able to do that, these guys basically propose step 2, which is query generation. The broad idea is that you take a document ID like 705 here and the tokens in it, you pass it to a separate, T5 model or a sequence-to-sequence learning model which basically generates different queries. So it's like a question generation model or a query generation model, which takes a document and generates many, many queries. When it does so, it basically creates a lot of query document pairs for every possible document in the corpus. So thereby essentially ensuring that you can train, a neural corpus indexer model such that it sees a lot of queries for the same document, and therefore it sees a lot of training points for the same document. Okay. Now, therefore, the last step essentially here in the training is to train by both the ground truth queries and the augmented query document pairs. So there is, of course, a ground truth query for this document, right? The green one, right? But then there is also these augmented queries in the purple one, which basically act as extra additional labeled data, labeled query document pairs to train the NCI model. Okay. So as you see, the NCI model is basically trained as follows. You essentially have generated or ground truth queries. You pass them to the encoder, and then you pass them to the decoder, and then the decoder hopefully generates the ground truth document ID. If it doesn't generate the ground truth document ID, of course, you backpropagate the cross entropy loss. Okay. So that's that. Now, of course, there are other things to discuss. For example, what is this consistency-based regularization loss? And also how are these? How is the cross entropy computed? Okay. So remember, and again, what is this? What is this power decoder? Right. So we will answer all of those questions one by one. So when the decoder is generating document IDs, it's generating them cluster by cluster. So essentially, for example, if it has to generate this document ID 705, well, it's going to generate 5 because that is the fifth cluster at the top level, then document ID 4, or the cluster ID 4, and then the cluster ID 2. Okay, so that's how it generates. So it basically, each of these things is basically, each of these cluster IDs is a token by itself. Okay, so it generates token by token. So essentially, if these are the representations, so this is basically like 5 and then 4, and then the 2 can be generated based on the previous few ones. X, of course, is the query. So X is, of course, the query. So the query is also passed as input, and then it's a autoregressive decoder generating the next ID. In the list which totally constitutes the document ID. Okay. So that's that. Now, to ensure that there is no overfitting, essentially in this encoder-decoder framework, besides the cross entropy loss, they also bring in something called the consistency-based regularization loss. So what they try to do is to essentially take the same query and essentially pass through the model with different dropout configurations, which basically means that the overall model will generate these two different output output logits. And then what they try to do is to ensure that if you have a batch, if you have a batch of say Q samples, and what you do is to actually try out for every sample in this batch of Q samples, you actually try out 2 different dropouts. So, and what you want to do is to basically minimize this contrastive regularization loss, which is essentially ensuring that if you use the same ith sample, right? So as to generate ZI1 and ZI2 using 2 different dropout configurations, their similarity should be higher compared to essentially using a document I along with a document K along with another document, right? So of course, if you use the same sample, its similarity should be higher even when you vary the dropout configuration. But if you have 2 different samples, its similarity should be lower. Right? That's basically that. So that's how they define the consistency-based regularization loss, in the hope of avoiding overfitting, right? So that's what we talked about. It basically uses that loss to avoid overfitting. Now, this is the same encoder-decoder framework that we saw on the previous slide. A little bit more details. So when you're generating, the IDs in the document, or those tokens in the document ID list, or the cluster IDs in the document ID list, you want to ensure that you use a beam search, a constrained beam search, such that you only generate valid identifiers. You know what documents are there. You basically know the document ID lists for each of those documents, and you could basically encode them into a prefix tree, or a trie kind of a framework, a trie kind of a data structure, such that whenever the beam search tries to generate the next token, it must generate a valid token only. Okay. Now, tokens basically So how do you basically represent tokens in this framework, right? So as I mentioned, tokens can broadly just be represented using cluster IDs at different levels, right? However, cluster IDs by themselves are not enough. So what you want to do is to basically, if you essentially want to, let's say, generate cluster ID R0, you should also prefix it with a position because, cluster ID 5 here is very different from the cluster ID 5 here, right, at the next level. So therefore, what they also do as part of tokens is to basically have a token which is a combination of the level, cluster level, and then the cluster ID, right? Cluster level and then the cluster ID. So that's basically that. Uh, the second thing, so essentially the idea being that the same token in the same position, the same token appearing at different places in the same identifier has different meaning, right? Different places in the sense, different cluster level has different meaning. So that's that, right? The other interesting part is the same token in the same position may have different semantics with different prefixes. Okay, let me tell you what this means. This basically means that you see. If you're basically trying to predict a cluster, predict a document as, cluster ID 2 and in a 3-level hierarchy, right? The document could be cluster ID 2, then the cluster ID 3 and the document number 5, right? On the other hand, you could also have the document ID 5 using cluster ID 1 at the top level and then the first cluster and then the fifth document there, right? Of course, these two are two different documents. These two are two different documents. And that is what is meant here. With the same token in the same position, the 5 was the same token in the third position, right? May have different semantics with different prefixes because the prefixes are different here, the semantics are different, okay? And that is why they basically come up with a revised decoder. So this decoder is not the usual transformer decoder. It's basically a revised decoder. And they basically call it the power decoder or the prefix-aware weight adaptive decoder. Prefix-aware weight adaptive decoder. Now, how does this work is the question. Okay. So the way this works is as follows. You basically have the stuff coming from the encoder. So essentially you have the cross attention. So that part is there. And this is the decoder blocks. So essentially you have like multiple layers, transformer layers of decoder, right? Um, of course, typically what you would do is to basically pass on the previous few tokens along with, the token really comprises of the cluster level and the cluster ID, right? So basically you pass those tokens one by one in a left shifted manner such that you basically start generating hidden states, which can finally lead to generation of those cluster IDs. So that's a typical thing that you would do. Okay. Now, of course, the way you would generate these cluster IDs or tokens at the output is basically by using the standard softmax over H1WI, H1W, where W is typically a fixed weight matrix. Right? But here in this case, they basically use different WIs. Okay. So the final output layer's weight matrix is basically different for different positions. Remember, a position here actually stands for the cluster level, right? So for different cluster levels, you use a different weight matrix. How do you come up with different weight matrices, right? So the way you come up with different weight matrices is by using a parallel block of transformer decoder layers. So basically, this one is a parallel block of transformer decoder layers. Sorry. So as you see here, this is basically a parallel block of different transformer decoder layers. So what does this do? This basically takes your same R0, R1, R2. So basically what is being passed as input is the same R0, R1, R2. Okay. And these blocks are basically giving out, weight vectors or other, giving out some vectors. Now they are not weight vectors actually. They're more like attention weight vectors. Okay. So in fact, this new decoder, as I can call it, the new transformer decoder block is represented as follows. So it basically takes the query embedding and the representations of the previous tokens, the previous predicted tokens in that senses, and comes up with the next token. So the next token here is not really mentioned here, but the bracket basically denotes the next token. Adaptive decoder basically outputs the next token. Now this token is actually multiplied by the weight matrix W. So as to essentially get the weight matrix for the next position. Okay. So the idea is that you would basically get this particular, adaptive decoder. Let's call that output as OI, right? So OI, and that's basically the O1. That's basically O2, and that's basically O3. These O's are essentially then multiplied by the W. There's of course a pre-trained W. You multiply these O's by the W so as to essentially get a W1, which finally you multiply with your H1 so as to get and apply softmax so as to get your R1. Okay, so that's that. So essentially, it's sort of adapting the weights based on the prefixes. So you see, R0, R1, R2 are like components in the prefix. So based on the prefix, it's basically adapting the weights to be applied, and therefore predicts the right token, right next token. Okay, so that's basically how the prefix-aware weight adaptive decoder architecture works. Now, lastly, let me talk about how does NCI perform. So they measured the performance over two different data sets, natural questions, and so that's the natural questions data set, and the other data set is, so the first data set and the second data set is TriviaQA, right? So natural questions contains 320K query document pairs, TriviaQA contains 78K query document pairs, and they basically they built different size of models, so basically using T5 base, T5 large, and an ensemble. They also experimented with the query generation with the fine-tuned model versus the query generation with a pre-trained model. So here, basically, these are basically showing with fine-tuned model, right, versus the pre-trained query generation model. The fine-tuned one is, of course, fine-tuned on TriviaQA or natural questions dataset. These are results over natural questions. These are results over TriviaQA at the bottom, right? Bottom right. Okay. And they compare with multiple other retrieval methods like DSI, SEAL, ANSI, BERT, BM25, and so on. And what you can observe is that an ensemble with query generation, which is fine-tuned, gives them the best recall values, and a really good MRR value also compared to other methods, other baseline methods. And that also holds onto the other data set, which is TriviaQA. Okay. How fast or slow this method is? Well, I mean, small, base, large. They basically train three different sizes of NCI models using T5. And you can observe with a beam size of 10, the latency actually is in a few hundreds of milliseconds with the large model. With the beam size 100, the latency is even more, right? Of course, larger beam size would basically lead to better results. However, the latency increases significantly as well. Okay, so in summary, in this video, I talked about neural corpus indexer, which is a very interesting way of thinking about retrieval rather than looking at sparse retrieval or dense retrieval. It's like saying, hey, my model can it act like an index by itself, right? So it's a novel document retrieval paradigm. It directly retrieves document IDs for an input query. And the main architectural difference is in the prefix-aware weight adaptive decoder, where the weight of the classification layer or the output layer is the one that is changed, right? Now, this model does not come with without disadvantages. There are problems with the model. So, for example, they experimented with small data sets which just contained 320,000 query document pairs and 78,000 query document pairs. If you really want to work with the indexes which are hundreds of billions in size, you would need a much more larger capacity model. Second, inference speed needs to be improved to serve online queries in real time. The speed is clearly not enough. 356 milliseconds is clearly not enough, especially for such a small query document corpus, right? And the third one, it's difficult to update the model when new documents are added to the system. New documents just keep coming in every time, every day, every millisecond, right? And updating the index, in general, there are many, many interesting methods of updating the sparse index, inverted indexes, or even the dense index, approximate nearest neighbor search, approximate nearest neighbor indexes. But updating this index would really mean training the model further, right? And that is very complicated. So although NCI is a very interesting method of essentially treating your model as an index, conceptually, but practically, it may just work for smaller document collections. Okay, so that's it for this video. Thank you for watching. Hope you liked the video. Connect with me on my LinkedIn or look at my search on my homepage. Thank you.